Hello friends. So today we are going to solve questions which are from the year 1993, 1994 and 1995. From 1993 there is only one question. From 1994 there are total of 3 questions, and from 1995 we have total of 5 questions. Therefore, in totality we are going to solve 8 questions. So the first question, it was asked in the year 1993, and it states that in the given figure, S is a monochromatic point source emitting light wavelength lambda 500 nanometer, a thin lens of circular shape and focal length 0.1 meter is cut into two identical halves L1 and L2 by a plane passing through a diameter. The two halves are placed symmetrically about the central axis SO with a gap of 0.5 mm. The distance along the axis from S to L1 and S to L2 is 0.15 mm meter, while that from L1 to L2 to O is 1.30 meter. The screen at O is normal to SO. Based on this, we have two questions. In the first part, it asks that if the third intensity maximum occurs at point A on the screen, find the distance OA. And B part, if the gap between L1 and L2 is reduced from its original value of 0.5 mm, will the distance OA increase, decrease, or remain same? So we are given this question. We have two halves of the lens. One half is of L1, another one is of L2. A single coherent monochromatic source, that is S1, is kept at a distance of 0.15 meter from the axis of the lens, and we have a screen which is at a distance of 1.3 meters, and the gap between the two lenses is given as 0.5 mm. So first of all, we are going to find out what will be this AO. Okay. And let us say this AO is our Y. So initially we are given this coherent source will be acting as an object. So we can write that the object distance that is represented as U is equal to minus 0.15 meter, and the focal length that is given to us F is equal to, this will be plus 0.10 meters because it is a converging lens. So based on this, or we can say based on using lens formula, we can find out the position of the image. So we can say 1 upon V is equal to 1 upon F plus 1 upon U, and this gives us, we substitute the values, 1 upon V is equal to 1 upon 0.10 minus 1 upon 0.15. This gives us that V is equal to 0.30 meters. Means it is going to form an image at a distance of 0.30 meters. So we can draw an approximate figure for that. and this is our central axis. We have screen, this is O, and this point is given as A. Let us suppose this distance which we are going to find out is given as Y. We have two lenses, one on the upper side and another one on the lower side. Upper side is our L1, lower side is our L2, and we are given a source that is our S, and this S is kept at a distance of, from the lens it is at a 0.15 meters, and the image that is being found by these lenses is at a distance of 0.30 meters. So let us suppose that is somewhere here. So this is our V is equal to 0.30 meters, and we can draw an approximate ray diagram for that, and it will be something like this. And similarly on the opposite side also. And this. So here we are going to have, let us call the upper one as S1 and the lower one as S2. Okay. And the distance we can say, okay, we'll see that later on. So this is our L2 and this is our L1. So now from the figure you can see now the single coherent source is now converted into two sources, S1 as well as S2. Okay. Now let's find out what will be the magnification and image separation. Magnification and image separation. Image separation means we have two images, S1 and S2. So what will be the distance between the two images? That is our image separation. And for magnification we can use the formula directly. Magnification, that is of M, is equal to image distance divided by the object distance, and that is 0.3, and here we have minus 0.5, and this comes as minus of 2. So it means the image will be inverted because of negative sign, and its size will be twice that of the object. So therefore we can say that image will be inverted and twice as large as the object. Now let's find out the distance between the separation between the images, and we are given that these two lenses between the gap is 0.5 mm, and so the distance between the lenses is given as 0.5 mm. So we have the distance, this distance is given as 0.5 mm, and let us call this as point A and let us call this as point B. Okay. And we can say okay, so here we can consider two triangles. one will be triangle SAB, and another triangle will be S1 and S2. Okay, so we can consider two triangles. One triangle is our SAB, and another triangle will be our this one. Okay. So you can say, considering triangles SAB and triangle S1, S2, these two triangles will be similar to each other. Triangle SAB is similar to triangle S1, S2, so their sides will be in ratio. Therefore, we can say that our AB and divided by 0.15 will be equal to S1, S2, and this will be 0.45. And AB is our, it is given as 0.5 mm. Okay, and we can ideally, because we can assume that this particular distance is quite negligible, so we can simply say that AB is ever equal to 0.5. And okay, so therefore we can write that this gives us 0.5 oblique 0.15 is equal to, let us suppose the distance between S1 and S2 is our D. So this is our D. So we can write this is equal to D, and this will be our 0.45. So this gives us that the D is equal to 1.5 mm. Okay, so this is the distance between two sources S1 and S2. Distance between two sources S1 and S2 given as D is equal to 1.5 mm. And next we are going to find out the fringe width. Fringe width calculation, or we can also say as interference, because now we have two sources S1 and S2, and these two sources S1 and S2 will be acting as a coherent sources. So you can see S1 and S2, they act as coherent point sources. Okay, and they are going to interfere on the screen placed at 1.30 meter from the behind the lens, and they interfere on the screen placed 1.3 meter behind the lens. So we can use the width formula, fringe width formula. Fringe width, that is our W, is equal to lambda capital D upon small d. And this distance from the sources, the total distance is this distance. It is given as 1.30. Yeah. So the distance from the sources to the screen, this will be coming as our 1 meter. And this is our capital D. So we substitute the values. Lambda is given to us in nanometer. So we can say this will be 5 into 10 raised to power minus 4 millimeter. D is our 10 raised to power 3 millimeter, and small d is our 1.5 millimeter. And we get that our omega, that is a fringe width, is 1.3 millimeters. And we have to find out the position of the third maximum. We can say that position of third maximum, let us suppose that is given as y of 3, and this will be equal to 3 times the fringe width, that is 3 into 1 by 3. This comes as 1 millimeter. Okay. That is, you can say the distance from central maxima to third maxima. Third maxima is, this point is given as A. So you can say this OA, third maxima, which means O to A will be given as 1 millimeter. Now we come to the second part, B part, which states that what happens when the gap is reduced by half. So we can say gap between L1 and L2, which is basically our AB, is reduced. Then separation distance between S1 and S2, which is basically our D, is going to decrease. And we can just clearly understand, because D decreasing, D means, okay, 1 second, what was asked? I forgot. Okay, it asks that what happens to the distance OA. It means what happens to the fringe width, third fringe width. Okay. So based on this, we can say that decreasing D means that fringe width, that is represented as W, increases. Now if it increases, we can say distance that is our OA, or which is our third maxima, will increase. So this was our first question, and now we come to the next question. Here it was asked in the year 1994, and it states that a narrow slit of width 1 mm is illuminated by a monochromatic light of wavelength 600 nanometer. The distance between the first minima on the other side of the screen at a distance of 2 meter is. So here we have to find out what will be the you can say the distance between the first minima on the either side of the screen, and we can use the directly formula. We can say the distance between the first minima on the other side of central maxima. Central maxima is given as y, and this y is our lambda L upon A. And it is usually written, let me write the standard one, it is written as capital D divided by small d, where d is the distance between the slits, and one second, I think, let me check, it is capital D upon small d. Here small d is the width of the slits, and capital D is the distance of slit to the screen, lambda is the wavelength. And if we can draw its approximate figure, so we always know that at the center it is always a maxima, something like this. So either side of this will be minima, and this will be also minima. Okay, and we have to find out this distance, or we can say we have to find out this distance, and this center one is always a maxima. So this is our always maxima. So we substitute the values, we get this as y will be equal to 600 into 10 to the power minus 9 multiplied by 2, and this is 1 into 10 to the power minus 3, and this gives us 1.2 millimeter. Okay. So it means the distance of central maxima to the first minima on one side. So it basically means that this is our y, which we just found out. So we can say the distance from central maxima to first minima is 1.2 millimeter on one side. So it means the total distance between the either side of the minima will be twice of y. So this will be coming as twice of y. twice of y. So total distance between first minima on either side this will be given as twice of y and will be equal to 2 into 1.2. This will be our 2.4 millimeter. So we have option number C is the correct one. Option C is correct. So we come to the next question. It was asked in the year 1994 and it states that two thin convex lenses of focal length f1 and f2 are separated by a horizontal distance d, where d is less than f1 and also less than f2, and their centers are displaced by a vertical displacement delta as shown in the figure. Taking the origin of the coordinate O at the center of the first lens, x and y coordinates of the focal point of this lens system for a parallel beam of rays coming from left are given by. So we have two lenses and we can say that let us call this as lens L1 and this is lens our L2. And we have to find out the coordinate of the focal point of the first, that is its x coordinate as well as y coordinate. So therefore, and we are given d as the distance of them, and let us draw a figure, approximate figure for that, and try to sort it out what actually it means. So we have a central axis, we have first lens, and it is given that the axis of this lens is acting as a origin. So this will be our y axis and this is our x axis. And second lens is having its axis that is shifted by delta. So we are going to have a second lens which can be approximately like this, and if the center of the second lens is this one and its axis is our here, so this distance is given as delta. And we have to find out with respect to the focus of first lens. So the d is the distance between the two lenses, so this is our d, and if we say that our f1 is the, you can say, focal length of first lens, so that means the image that will be formed by the lens L1, so let us call this as lens L1 and this is lens L2, will be formed at the focus. Okay, so let us draw a approximate figure for that. Okay. And it says that the rays will be coming parallel to the principal axis, which is our OX. Let us draw these two rays, and let me draw this lens a little bit smaller one, because otherwise the figure won't be coming good. So this it is focus somewhere, and this will be its principal axis, and we have distance. This distance is delta. So if this ray just passes through the focal, you can say this center from here, and it will be landing somewhere here, and the other one is going to converge for this point. And it will be converging this direction. And similarly, we can draw from the bottom side also. And this will be focus. So we can say this distance is our f1, and we can say distance from lens L2 to focus f1 will be our f1 minus d. And for the time being this looks good. We can just modify if require something else are required. So we have to find out what will be the coordinates of this particular point. So we can say we have two convex lenses. Two convex lenses, and like I said that the focal length of first lens, so first lens, it has a focal length of f1, and this is first lens is centered at O, centered at O. Now we have a second lens, and let us suppose its focal length is f2, and it's placed at a distance d from the first one, placed at a distance of d, and the first lens we are calling as L1 and second lens we are calling as L2, d from L1. An important part is that there is a vertical separation of delta, having vertical separation of delta. Therefore, we can find out that the first lens, the rays are coming as parallel, so the light will be focused at a distance of a focal length, that is our f1 for lens number 1, that is our L1. So you can say for first lens, parallel beam of light, focus at its focus, that is f1, or we can also say that at a distance of f1 from O. Let us suppose the image that is forming here, we are going to call it as I1. Now this I1 is going to act as a virtual image for lens L2. So this I1 will be acting as a virtual image for our L2, and for that we can further draw an approximate figure. So this will be acting, so it will be going somewhere here, and this one, so this will be close to here, this will be I2, not the exact one, but approximate it will be here. Focused at focus, forming an image I1. Resulting image I1. You can say this I1 image, this I1 acts as virtual object to second lens, which is we are calling as L2. Okay. Therefore, for L2, the object distance, which is our u, will be equal to plus f1 minus d, okay, and its focal length will be our plus f2. Therefore, we can find out the distance of the image for lens L2, and we can say 1 upon v is equal to 1 upon f plus 1 upon u, and this gives us 1 upon f2 plus 1 upon f1 minus d. So this gives us that the image v, it will be our f2 into f1 minus d divided by f2 plus f1 minus d. So this will be the x coordinate of our focal point. Sorry, not this one, but a d plus v will be the x coordinate. So therefore we can say that x coordinate of focal point will be x, which is our d plus v. It gives us d plus v is our f2 f1 minus d f1 plus f2 minus d. And we can just solve it further, and we can write this as x is equal to f1 plus f2 minus d, and it will be coming as f1 f2, and this will be d times f1 minus d plus d times f1 minus d. So this is our x coordinate. And now we can find out a linear magnification for L2. Linear magnification for L2, and which is given as m, and m will be equal to v upon u. So therefore we can write our m is equal to v, we already know, we just found out, is our f2 multiplied by f1 minus d, denominator is f1 plus f2 minus d, and our u is f1 minus d. So here f1 minus d cancels out, so this comes as f2 upon f1 plus f2 and minus of d. Therefore we can say, and also we also know that our magnification m is also equal to, if we can write this as I2 upon O. O is our distance, so this comes as I2 upon delta. Okay. So this gives us that our I2 will be equal to, we just found out our magnification, which was our v upon u, so this comes as m times delta. Now we substitute value of m, so this gives us that our I2 will be equal to f2 upon f1 plus f2 minus of d and multiply by delta. And this is nothing but, so we were having, the figure is, so the distance for total was delta, and we found out this distance. So this is our just below the, so the ultimately the y coordinate will be delta minus this distance which we just found out. So we can say that our y coordinate of focus is delta minus, and we just found out is f2 delta f1 plus f2 and minus of d, and we can just solve it further. This gives us f1 plus f2 minus of d, and this will be coming as f2 delta cancels out, so comes as delta times f1 minus d. So this is our y coordinate, okay, which we were supposed to find out. So the option that is the correct one is our y coordinate is our this one, and the x coordinate was our, so option number C is the correct one. Option C is correct. So we come to the next question, and it is a simple ray diagram for this question. It was asked in the year 1994, and it says that an image y is formed for a point object x by a lens whose optic axis AB as shown in figure. Draw a ray diagram to locate the lens and its focus. If the image y of the object x is formed by a concave mirror having the same optic axis AB instead of lens, draw another ray diagram to locate the mirror and its focus. So we have object x and we have corresponding image y. In the first case, it is the image y is formed by using the lens, And in the second case, image Y is found by using a concave mirror. So we have to draw its ray diagram. Okay. So let us draw first of all for the lens, and we are given the principal axis, which is our AB, and an object, point object rather. So this is, let us suppose, our point object, that is our X, and let us draw this lens. It will be somewhere here, and the ray for the Y, it should be directly crossing from here. It should be, this should be our point Y. And another ray of light which should be coming parallel to the principal axis will pass, and this will be our formation of the image. So this is our concave lens, lens. Yeah. And next is we are for concave mirror. And once again we have the same principal axis, that is our AB. So this is our AB, and we have an object, that is our X. Image we already know is our Y, and this is our concave. So therefore, and it will be passing through the focus. So this will be our focus F, and other one will be passing through the center of curvature, and here we are going to get this will be the center of curvature, and this will be our Y. So this for concave mirror. It requires straightforward. Next question. It was asked in the year 1995, and it states that an isosceles prism of angle 120 has a refractive index of 1.44. Two parallel rays of monochromatic light enter the prism parallel to each other in the air as shown. The rays emerge from the opposite face. So there are four options. First one is parallel, second diverging, and last two is the angle which is they are forming with each other. So for that we have to draw a approximate ray diagram. So let's draw the approximate ray diagram for that. And let us suppose this is our prism, and we have a principal axis this way, and this is symmetric but not looking like a symmetric. Hopefully this one works. Okay. And we have two rays which are coming parallel to each other, and they are striking this surface. Let us suppose this is surface A, this is B, and let us call this as C, and this angle is given as 120. So as it is striking the surface AB perpendicularly, so ideally it will be passing through this almost in a straight line. And let us draw the perpendicular to this surface AC. So because of that it will be bending away from the normal, something like this. Similarly, we can draw the perpendicular at other point. Let us call this as P and this as our P prime, and it will be also bend and meet at somewhere here. And we have to find out the angle between them. Okay, it is diverging, and angle between, obviously it is not diverging, and neither they are parallel with each other. Okay, they are converging, so it means we make an angle, so we have to find out this angle, what they are making with each other. So therefore, this will be our angle of incident, and this will be our angle of refraction, and we can also draw the deviation. So this will be, sorry, this will be coming almost, this will be our R, and ray will be coming almost parallel, so this will be our deviation angle, that is our delta. And similarly, we can draw on other side also, and we are going to have this will be our delta. So we have 120, so this angle we have 60, and this will be also 60. So this angle is 60, so that's why we are going to get that the angle, this angle will be 60, and similarly there will be 60 on the other side also, okay, with respect to the lens. Because everything is symmetric with each other. So we can say that from ray diagram, we can write that the angle CP, and let us, this is a C and this is our P, and let us call this as our P, and let us call this as P prime. Oh, sorry, P prime we already have, so let us call this as X and this as Y. So we can say that our angle, and we have two parallel rays, let us call this as R1 and this called as R2. This looks okay now. Okay. So we can say that our angle, we have our angle CPX, okay, angle CPX, okay, this angle CPX, so this angle is just vertical opposite to the 60 degree, so this will be our 60 degree, okay, and this will be also equal to our angle R1P, and we have our A, because we just found this is our angle R1P and A, and similarly it will be in the opposite side also, and we can say similarly second angle is our C P prime, and that is our Y. So now we can find out our angle of incident. We can say the angle of incidence, which is our I, is equal to 90 minus, and we have this as R1PA, which is about 60 degree. So we get our I1 is equal to 90 minus 60, giving us 30 degree. Now we can use the angle Snell's law. Snell's law, which is going to help us to find out the angle of refraction. And Snell's law states that sine of incidence upon sine of refraction is equal to n2 by n1. And n1 is our here, you can see initial medium, and n2 is our final medium. Okay. So you can say our n1 is our initial medium and n2 is our final medium. So we can use this for ray R1P. So we can say for ray R1P, incident we just found it is our 30 degree. So we can say sine of 30 upon sine of R will be equal to, this is air upon the refractive index of the, that is a prism, that is 1.44, and this gives us that sine of R will be equal to, this comes as 1.44 and divided by 2, this gives us that R is equal to sine inverse of 0.72. So we found out the angle of refraction, and we are mainly interested in the angle which the rays are making with the horizontal, because R1x is parallel to our principal axis. Okay, so this is our principal axis. Let us call this as SS1, and this A, or we can say delta, so this will be angle delta, and accordingly we are going to have this angle will be also delta, and reversely for the other side also same. So the angle between the two rays, this entire angle will be coming as twice of delta. So I am mainly interested in angle delta, and delta is our deviation. Okay. So we can say that the standard formula is delta is equal to R minus I, which gives us sine of 0.72 minus of 30 degree, and let us call this angle as theta. This angle is theta, so theta will be equal to twice of delta. So therefore we can say that our theta is equal to twice of angle delta. So this was angle delta, so this gives us twice, and we have here sine inverse of 0.72 and minus of 30 degree. So therefore angle with each other is option number C is the correct one. Option C is correct. So we come to the next question. It was asked in the year 1995, and it states that the focal lengths of the objective and the eyepiece of a compound microscope are 2 cm and 3 cm respectively. The distance between the objective and the eyepiece is 15 cm, the final image formed by the eyepiece is at infinity. The two lenses are thin, the distance in centimeter of the object and the image produced by the objective measured from the objective lens are respectively. So here we are given the focal length of object and eyepiece and distance between them. And the important part is that here it is mentioned that the final image is formed at infinity. And if the final image is formed at infinity, so therefore final image means because of both objective and eyepiece is at infinity. Therefore, the eyepiece must form an image at its focal point. Okay, so that's the most important part here. So we are given the focal length of objective, that is our f naught. This is our 2 centimeter. Focal length of eyepiece, that is our fe, is 3 centimeter. Distance between the two, that is our L, is 15 centimeter. And we have to remember that final image is at infinity. So therefore, we can draw a conclusion that for eyepiece must have image at its focal point. Image at its focal point. So let us start from this eyepiece condition only. For eyepiece, you can say so therefore you can write that the image formed by objective must be at a distance of fe, and that is our 3 centimeter from the eyepiece. So it means the image formed by objective it will be given by L minus Fe. So we substitute the values and this gives us 15 minus 3, and which is our 12 centimeter, and this is from objective. Now we are going to find out the final object distance. Final object distance for objective. So we can use standard formula 1 upon V minus 1 upon U is equal to 1 upon F. So we substitute the values, we get this as 1 upon plus 12 minus 1 upon U, and this comes as focal length is given as 2, so 1 upon 2, and this gives that our u is minus 12 upon 5, which is equal to minus 2.4 centimeters. So the option that are correct is the objective distance is 2.4 and the image distance is 12 centimeter. So this option number A is the correct one. Option A is correct. So we come to the next question. So here it was asked in the year 1995 and states that in an interference arrangement similar to Young's double slit experiment, the slits S1 and S2 are illuminated with a coherent microwave source, each of frequency 106 Hz. I think it should be 10⁶ Hz. The sources are synchronized to have a zero phase difference. The slits are separated by a d 150 meter. The intensity I theta is measured as a function of theta, where theta is defined as shown. If I naught is the maximum intensity, then I theta for theta that varies with 0 to 90 degree is given by. So we have to find out the I theta, which is a measure of function theta. And here the angle theta is, this is the figure, two sources S1 and S2. Distance between the two sources is total distance is d. So from the central axis will be d by 2 and d by 2, and the theta angle is your angle of we can say observation from the central axis. So this is central axis and we have this as angle theta. Okay. So we can use directly the formula for the interference intensity. So we can say interference intensity which is given as our I theta will be equal to I naught, that is the maximum intensity cos square, and this comes as pi small d, and we have a sine of theta divided by lambda. Okay, so this is the basic formula for the interference intensity, and it is given that they have a zero phase difference. Okay, so we can write that zero phase difference. And the wavelength, we can easily find out, frequency is given to us. So we can say the lambda is equal to c upon f. C is the speed of light, that is 3 into 10⁸ meter per second, 10⁶. So this gives us the wavelength is about 300 meters. So we can substitute, we get our I of theta is equal to I naught cos square, and this have pi multiplied by 150, and this is our sine of theta, and divide by 300. So we get this as I of theta is equal to I naught, and this will be our cos square, and we have pi by 2 sine of theta, and we can just choose the value of theta which are given 0, 30 and 90, and last one is for all value of theta it will be constant, so which is not actually the case because I theta is dependent upon the sine of theta, that is theta. So this will be the wrong option. So let us check for theta is equal to 0. can say for theta is equal to 0, we are going to have sine of 0 sine 0 will be over 0, and this gives us cos square pi by 2 multiplied by 0, which is cos of 0, cos square of 0, and that will equal to 1. So it means that our I theta will be equal to I naught multiplied by 1, and this is equal to our I naught. Okay, so let us check for theta is equal to 0. So this option is correct one, that is C is the correct one. Okay, and we also say that this is our maximum intensity. Maximum intensity. Now next is theta is equal to 30 degree. So our sine 30 is our 1 by 2, and we find out our cos square, and here pi by 2 multiplied by half. This comes as cos square pi by 4. Cos pi by 4 is 1 by square root of 2. Its square will be equal to 1 by 2. So this comes as 1 by 2. And therefore, we can write our I of theta, or let us, for theta is equal to 30 degree, we get this as 1 by 2 I of theta. So for 30, option number A is also correct. And finally is for theta is 90 degree. So theta is equal to 90. And from here we can say our sine of 90, which is equal to 1, and this gives us cos square pi by 2, and this will be equal to 0. Therefore we have that I of theta at theta equal to 90 is equal to 0, and the option that is B is incorrect one. So A and C are correct. You can say option A and C are correct. Option A and C are correct. So we come to the next question, and it was asked in the year 1995, and it states that a ray of light traveling in the air is incident as a grazing angle, incident angle that is 90, on a long rectangular slab of transparent medium of thickness t is equal to 1 meter. The point of incident is the origin A00. The medium has a variable index of refraction, that is our ny, given by this particular equation, where k is 1 meter raised to power minus 3 by 2. Refractive index of air is 1. So based on this description, we are going to find out these 4 questions. First one is, obtain the relationship between the slope of trajectory of the ray at a point B in the medium and the incident angle at that point. B is, obtain the equation of trajectory yx of the ray in the medium. C is, obtain the coordinate x1 y1 at P where the ray intersects the upper surface of slab boundary. Indicate the path of the ray subsequently. So first of all, we are going to find out the slope of the trajectory at a random point B. Okay. And we have to keep in mind that here the refractive index is a function of y, because k is rather, we can say, constant, and it's, so therefore it is depending upon the y, but the y is, you can say, along the not directly dependent, but raised to some fractional ratio, fractional power. Okay. So here we can draw an approximate figure for that, part A. And let us suppose this is our x-axis and this is our y-axis, and ray of light is incident at A and its coordinate is given as 0, 0, and it just grazes this point A. So this, you can say, angle is close to 90 degree. And it will be traveling something like this, and a random point B is, let us suppose, here, and its coordinate is given as x comma y. And if we draw a tangent to this point, and let us suppose that tangent is like this, tangent is making an angle of theta with the x-axis, and we can draw this one. So this we are going to have that this will be our angle of incident at this particular point. So we can say for part A, we have to remember that refractive index is a function of y. The refractive index is a function of y. That is, it is only going to vary in y-axis. That is, it varies along y-axis. And secondly, it also says from the equation that as our refractive index increases, y also increases. You can say as our refractive index increases, y also increases. So therefore, we can say that the ray of light is traveling from the rarer medium to the denser medium, and it will be bending toward the normal. Okay, and shape will be, we can just finalize the shape later on also, it's not a big issue. Okay, so from here we can say that a ray of light will travel from rarer to denser medium, and which means that it will bend towards the normal. So here we can just draw an approximate of this. Within the glass slab, you can say that if these are the various layers in the glass slab, and this will be our rarer medium, and for this rarer medium the next one will be our denser medium. But for this denser medium, next medium will be more denser. Okay, so we can say if this is our, so it means that if we have these 3 layers, or we can say 4 layers, then this is denser D1, D2 and D3, and their density is going to increase in this way. So it will be getting denser, denser. So previous one will be always rarer. So this is the main. So that's why it is going to bend always towards the normal. And now we can find out the angle incidence, that is angle of I. So therefore you can say the incidence angle at B, that is our I, the incident angle at B, if that is given as I. So based on this, let me draw it here. So this is our x-axis, and we have our, this is our point B, and this angle is our theta, and this is our angle I, and this is our 90 degree. So we can say that theta is equal to 90 minus I. So we can say our theta is equal to 90 minus I. And from here we can say that tangent of theta will be equal to tangent of 90 minus I, which gives us a cotangent of I. Or we can say tangent of theta is nothing of a slope. So we can write that the slope is equal to cotangent of I, that is our angle of incident. Now we come to the next part, and for that we are given that at y is equal to 0, that is our point A, we have refractive index at A is equal to 1, that is basically our air. And it is said that light enters grazing incident. We can say angle of A is our 90 degree, that is given to us. So from here we can say initially light travels, so this is our point A. So light travels parallel to x-axis. This we can draw from here. And we also know that the slope of trajectory is given by dy by dx. You can say that the slope of trajectory is given by dy by dx, or we can also say this can be represented as tangent of theta, which is also our dy by dx. And we just found out that is our cotangent of I. Now we can use the Snell's law at point A and at point B. Snell's law, and this Snell's law for point A, where y is equal to 0, and point B, where y is greater than 0. So we can write this as our refractive index NA, sine of IA is equal to refractive index at point B, and we have the sine of IB. And at point A, we already know that our NA is equal to 1 and the angle of incident is our, that is IA, is our 90 degree. And at point B, we already know the equation for the refractive index. So we can say at point B, that is our NB. The equation is given as, cos value of K is 1, so NB will be equal to y 3 by 2 plus 1 and its square root. So we are going to have this as y 3 by 2 plus 1 and whole raised to power 1 by 2, because K is already 1. And IB is our incident angle. So we substitute the respective values. We get sine 90 is our 1, so this comes as 1 multiplied by sine of 90. NB is our y raised to power 3 by 2 plus 1 and this comes as 1 by 2, and sine B is our sine of I. So therefore we get sine 91. So from here we can write that our sine of I will be equal to 1 upon y 3 by 2 plus 1 and whole raised to power 1 by 2. And we already know that cot of I is our cos I upon sine I. So we are going to express cot I in terms of y basically. So we are going to express cot I in terms of y. So we know that our cot I is cos of I upon sine of I, and we also know sine square I plus cos square I is equal to 1. Sine we just found out, so we can say that we can write it as cos of I will be equal to 1 minus sine square I and its square root. We substitute sine of I. So we get this as cos of I is equal to 1 minus, square cancels out the square root, so we get this as y 3 by 2 plus 1 and its whole square root. So we take the LCM, we get this as y 3 by 2 plus 1 and y 3 by 2 and its whole square. Now we easily find out our cot of I, because now we know cos of I, sin I we already know it. So we can write our cot of I will be equal to sin of I is 1 upon square root y 3 by 2 plus 1 and cos of I is our y 3 by 2 its square root and square root of y 3 by 2 plus 1. So these two terms cancel out. So this gives us y 3 by 2 and its square root. This gives us y 3 raised to power 4. Therefore, we know that our cot of I, which was equal to dy by dx, is equal to y raised to power 3 by 4. And we can further solve this differential equation. So from here we can write that our dx is equal to y minus 3 by 4 times dy. This comes to 0 to x dx, and we come to 0 to y, because initial coordinate for both x and y is 0 and final coordinate is x and y. This comes to y minus 3 by 4, and we have this at dy. So we get this as x is equal to we are going to have this as y 1 by 4 and divided by 1 by 4. Limits goes from 0 to y. So this gives us that our x is equal to 4 times y raised to power 1 by 4. So this is our equation for trajectory. This is our equation for trajectory. Okay. And from here we can just make a physical interpretation of this, that our x is, because 4 will be constant, is raised to power 1 by 4. So it means that the light bends gradually in the medium. Light bends gradually in the medium. Okay. And this, you can say, this type of typical behavior is also sometimes called as a, for the optics which has a particular name, it is called as a graded index optics. So you can say that so from here we can also say as y increases, the refractive index which is a NB increases. Therefore light ray curve away from the vertical. Away from vertical. Okay. And we can also say slower speed at higher y. Slower speed at higher y. This will be helping us in to draw the final, you can say, shape of the ray. And we can also say that this is called as graded index optics. Index optics. And finally we have to find out the coordinates of the point, that is our point of emergence. Coordinates of point of emergence. And for that we can draw an approximate figure, or we can say the ray diagram. And we have so this is x-axis, the y-axis, and the glass slab is having a thickness of 1, which is something like this. So this is given as 1 meter. And initially the ray enters at approximate angle of 90 degree, and as we continue to move upward, and the value of refractive index is subsequently going to increase as y increases, but as y increases the ray tends to bend away from the normal and it will be going something like this. So we have to find out this particular point. And B, we already said it's somewhere here. This is our B having coordinate x comma y, and this is angle theta, and we have this as A, coordinate is 0 comma 0, and this is our air, and this is a medium, and this is again our air. So we are supposed to find out the coordinate of the point of emergence. Okay, 1 second, sorry, drew it wrong. So it will be going somewhere like this. So we have to find the point of emergence. Let us, this is A, let us call B, this was our B, let us call this as point as C. So we have to point out the point of emergence, that is point number C. That is our point C. And we already know the equation of trajectory. Equation of trajectory. This gives us that our x is equal to 4 times y raised to power 1 by 4. And the ray will be exiting the slab when y is equal to 1. Okay. So this is our y coordinate, which is equal to our 0 comma 1. So we can say that ray exits the slab at y is equal to 1. So from here we can find out the coordinate of x. So therefore x will be equal to 4, 1 raised to power 1 by 4. This gives that our x is equal to 4 meter rather. So therefore you can say point C is going to have a coordinate of 4 comma 1. So we did option A and did B, and okay, this point is called as P, okay, which I call C. So this we also found out. So indicate the path of ray subsequently. Okay, we have to find out the path of this. So let me correct one thing here, that this point is our C, not P. So this is point P. So this we can write point P, and this is our point P. So we found out this coordinate is our 4 comma 1. Okay. Now we have to find out the emergence at point P. You can say grazing emergence at point P. We can use Snell's law at point P. Snell's law at P, and the emergence is at P, and refractive index, it will be NP will be equal to 1. Okay. So we can say Snell's law at P. So we can write that as NA sine of IA will be equal to NP sine of IP. NA is our 1, IA is our 90 degree, and NP is also our 1. Okay. So we can write this as, this is our 1, 90 degree as well as 1. So we can say that our 1 sine 90 is equal to 1, and we have this is sine of IP, and this gives us sine 90 is 1, so sine of IP is also equal to 1, which gives us that our IP will be our 90 degree. So it means the emergence ray will be approximately parallel to the boundary, okay, just as it enters. So entering as well as leaving both will be parallel to the x-axis. So we can say that a ray emerges parallel to boundary, or we can also say our x-axis, which we are calling as a grazing emergence. And I think this was the only thing that was asked here. Yeah. So I think this completes. Yeah, this is done. So these were the questions. The total of, you can say, 8 questions that was asked from the 93, 94 and 1995. So this completes all the 8 questions. Thank you.